Welcome. In this video, we're going to use the graphs below to identify absolute extrema if they exist for each function, and if they exist is key since not all of these will have absolute extrema. So this first one, a of x equals x cubed, on all real numbers has no absolute maximum and no absolute minimum. What about our next function? B of x equals x divided by 2 minus x, and the domain here is restricted from negative infinity to positive 2, but if you notice, this goes off in the y direction forever, and this goes off in the negative y direction forever. So this one will, again, have no absolute maximum and no absolute minimum. Next, c of x is equal to cosine of x, and again, the domain here is all real numbers. If you notice, we have absolute maximums at several places and absolute minimums at several places. If you notice, the absolute maxima occur at even pi values. So here I have 2 pi, here I have 0 pi, negative 2 pi, and so on. The absolute minimums occur at odd values of pi. So here's negative pi, here's positive pi. How can we write that out? Our absolute maximums occur at x equals 2k pi, where k is an integer. If you need a refresher on integers, there are all the positive whole numbers, negative whole numbers, and 0. And this lovely symbol is used to represent the integers. All the absolute minimums occur at odd values of pi. So they occur when x equals 2j plus 1, this entire quantity multiplied by pi. And in this case, j is an integer. Next, I have d of x. So 4x times x squared minus 1, quantity squared, and this is again on R. There is no absolute maximum and no absolute minimum since we're going up and down forever. Next, I have f of x equals x minus 2 squared, and here the domain is restricted. If we didn't restrict this domain, so say this wasn't restricted, this would just go on and on in both directions, and we would have no absolute maximum, but we would have an absolute minimum here. But since we restricted our domain, we have both an absolute maximum and an absolute minimum. The absolute maximum occurs here when x equals 4. The absolute minimum occurs here when x equals 2. Finally, g of x should look familiar, and I'm going to move the notes a little bit to refresh your memory. G of x looks familiar because it is the function identical here to b of x. The only difference is I've restricted the domain a bit more, actually a lot more. Our previous domain was from negative infinity to positive 2. Now I'm including from 0 to 2. That's it. So it is almost the same graph. As you can see, it is just restricted. So from here onward. So now that does change things. We suddenly have an absolute minimum here at x equals 0, but we still have no absolute maximum since g still grows without bound as it reaches its vertical asymptote at x equals 2. So now here are all the graphs. And the big takeaway you should have from here is that not every graph has absolute extrema. And sometimes you can force a function to have absolute extrema when you restrict its domain, as we did here for g, and as we did here for f. Now let's answer this last question. Do any of the graphs above have local minimum and maximum values that are not absolute extrema? Absolutely. If you take a look at D and F, they both have extrema that are not absolute. Let's take a look at D first. D has local minimums here at about negative 0.45 and at 1. D also has local maximums at negative 1 and positive 0.45. Now let's look at f. If you notice, f had an absolute maximum here at x equals 4 and an absolute minimum at x equals 2, but we also have this local maximum at x equals 1. And since every absolute minimum is also a local minimum, we also have a local min here at x equals 2.